Welcome to Geometry Essential Standard 2, Learning Target 4 over conditional statements. This is a different type of learning. It's not your typical math lesson. This is more about logic and how things work together to prove something true or prove something false. So a conditional statement is a statement that can be written in the form if P, then Q. So if an animal is a blue jay, then it is a bird. So that would be a conditional statement. So if you work hard, then you will get a good grade. That is also a conditional statement. Conditional statements can also be false. So if you're over 7 foot tall, then you work really hard. That's not necessarily a true conditional statement, but it's still a conditional statement because it's written in if-then form. The hypothesis is the part P, so it's the part that comes after the word if. Notice that it does not include the word if, it comes after the word if. The conclusion is the Q part. It comes after the word then. In symbolic form, we write it as P arrow Q, and we read that as P implies Q, or if P, then Q. In a Venn diagram, P is the small circle, and Q is a circle that P is contained inside. So here at the bottom, write a conditional statement from the following. All vertebrates have backbones. So every single vertebrate has a backbone. So vertebrates would be the small circle. Backbones is the outer circle. So as an if-then statement, we would say if an animal is a vertebrate, then it has a backbone. So our hypothesis would be an animal is a vertebrate, and our conclusion would be it has a backbone. So an obtuse triangle has exactly one obtuse angle. So here we know that if it is an obtuse triangle, so we wouldn't want to use the word it. So instead of saying if it is an obtuse triangle, we would say if a triangle, because that's the object that we are talking about. So if a triangle is obtuse, then it has exactly one obtuse angle. Identify the hypothesis and conclusion of each conditional. So I'm going to do the hypothesis in yellow. So on this first one, if today is Thanksgiving Day, then today is Thursday. The hypothesis is today is Thanksgiving Day. The conclusion I will do in green. So today is Thursday would be your conclusion. A number is a rational number if it is an integer. If we wrote this as a true conditional statement, we would say if a number is an integer, then it is a rational number. So our hypothesis is it is an integer, and our conclusion is a number is a rational number. So sometimes the conclusion can come before the hypothesis. Write a conditional statement from the following. So our blue jay is on the inside. Every single blue jay is a bird, and we've got other birds like cardinals and orioles that are part of birds but are not blue jays. So write a conditional statement from this statement. It would say if an animal is a blue jay, then it is a bird. And we're done with our conditional statement. Now we're going to talk a little bit about truth values. So the truth value is just telling us overall is if the statement is true or false. We can show infinite examples of something being true, but if we can show one example of it being false, that makes the statement overall have a truth value of false. So let's look at a couple examples. If this month is August, then next month is September. Well, we know that every time that we have the month of August, so every time that I make the hypothesis true, the next month is going to be September. That after August always comes September, so this is always true. If a number is odd, then it is divisible by 3. Well, I could come up with some examples of that. So some examples would be like the number 3, or the number 9, or the number 15. Those are all odd numbers that are divisible by 3. But I can also show that this statement could be false. If we think about the number 6, 6 is not odd, but it is divisible by 3. That is not a counterexample, because a counterexample has to make the if part true and the then part false. So I needed a number that is odd, but is not divisible by 3. So a counterexample would be like the number 5. The number 5 is odd, but 3 does not go into it evenly. So then we get to a little bit of truth value tables, and these can be confusing. The first two are very important, so you should know those. The last two are slightly confusing. Those are more just for advanced students, and I hope that you can understand them after I explain them. So the first one says that if I make the hypothesis, remember P is the hypothesis and Q is the conclusion. If both the hypothesis and the conclusion are true, then I know the truth value of this statement is true. So if he is a teacher, then he has a teaching certificate. If both parts are true, I know that the overall statement is true. If I make the hypothesis true and the conclusion false, so this is a lot like number 2 on the last screen, then I know that it has a false truth value, because that is our counterexample. So if he is a teacher, then he's a firefighter. So Mr. Starks is a teacher, he's not a firefighter, so that makes that statement a false statement. These last two, like I said, are kind of confusing here. If you make the hypothesis false, it does not matter what the second value is, it will have a truth value of true because it does not prove the statement false. So we give these examples. If pigs can fly, then the world is round. The world is round, but pigs can't fly. But we don't know if pigs can fly, or here in number 4, if pigs can fly. So in our world, in our reality, pigs cannot fly. But if we were in some reality where they could, we don't know what the result of the world would be, so we assume that it has a truth value of true until we can prove otherwise. The converse. I always relate these to shoes because Converse is a popular type of shoe. A converse is formed by changing the hypothesis and conclusion. I always call these shoes on the wrong foot. So in other words, we're simply taking off our shoes and putting them on different feet. So we're switching where our P and our Q go. So this is saying if Q, then P. So write the converse of the following conditional statement. If you scored lower than a 2.5 on your ES1 assessment, then you should retake that learning target. So the converse would say if you should retake that learning target, then you scored lower than a 2.5. on your ES1 assessment. what is the truth value of the conditional and the converse. So of the original conditional, if you scored lower than a 2.5 on your ES1 assessment, then you should retake that learning target. We should all agree that that is a true statement. That if you got a C, D, or F on your ES1 assessment, you should retake that so that way you gain that knowledge and can have a chance at doing well in the rest of the class, because that was really foundational learning that we had there. For the converse, so the converse says if you should retake that learning target, then you scored lower than 2.5. Well, they're saying that everyone that should retake it had to score lower than a 2.5. We could definitely have someone that wants to retake it that maybe got a 2.5 or a 3, but wants to get an A in the course, so they're going to retake it so that way they can have a better chance at getting an A. So the original conditional has a truth value, but the converse has a false truth value. Perpendicular lines. So if two lines intersect to form a right angle, then they are perpendicular lines. The definition can also be written using the converse. So they're going to switch the if and the then part. So if any two lines are perpendicular, then they intersect to form a right angle. So as a little bit of an FYI, you can use this upside down T here to write that line L is perpendicular to line M. If a conditional statement and its converse are both true, so both have a truth value of true, then the statement can be written as a biconditional. Biconditional, remember bi means two, so biconditional goes two ways. So if P implies Q and Q implies P, means that we can put P if and only if Q. So the double line, or the double arrowed line, means if and only if. So we could say P if and only if Q. That indicates that both P implies Q and Q implies P are true. So the converse of the definition of parallel lines would say if two lines are parallel, we use the symbol for parallel there, then they lie in the same plane, and do not intersect. Notice how I did not use the word it in my very first part of the if. So I replaced the word they with the thing that I was talking about, which was two lines. So then the biconditional, since both the definition and the converse are true, I can write it as a biconditional. And the biconditional can go in the order of the definition or the converse. It does not matter at all. I will use this one. I'll go off of the definition. So the biconditional does not start with the word if. It'll start off just with the subject of two lines. So two lines lie in the same plane, and do not intersect. If and only if. So biconditional is the biggest word. It has the three words with it. The three words are if and only if, so four words. If and only if they are parallel. Sorry, my Smart Notebook's messing up a little bit. Write the converse and biconditional statement from the conditional statement. So the converse of if points lie on the same line, then they are collinear. The converse would say if points are collinear. So I'm simply taking this part, but I replaced they with points. Then they lie on the same line. That's the converse. Now the biconditional, since both the conditional and the converse are true, I can write it as a biconditional. And I would say points are collinear if and only if they lie on the same line. Negation of the statement P is not P. It's written with the tilde sign, so that's the way that we'll write it in symbol form, and it simply means to either add the word not or to take away the word not. So the negation of I like eating cereal for breakfast is I don't like eating cereal for breakfast. So the negation is a lot like saying the opposite of what you want. So today is not Tuesday. The negation of that would just simply say today is Tuesday. As we would never say today is not Tuesday. So we simply take out the word not there. Conjecture. Conjecture is a statement you believe to be true based on inductive reasoning. Another way that I would say that is it is an educated guess. A counterexample is a specific example that you use to prove that a conjecture is false. Remember, this makes the hypothesis true and the conclusion false. Show that the conjecture is false by finding a counterexample. For every integer n to the third is positive. So we could also say if n is an integer, then n to the third is positive. So first thing that we need to remember is what an integer is. Integers are 0, 1, 2, 3, on forever. So they're your non-decimals. But they also include the negatives, so -1, -2, -3, on forever. So if I would take 2 is an integer. Is 2 to the third positive? Well, if we plug it into our calculator, 2 to the third power is 8. So that's actually an example. If I plugged in 0 is an integer, and 0 to the third power is still 0, which is not positive. So one counterexample would be 0. Another counterexample would be like -1. -1 to the third power is -1. Or -2 to the third power is -8. So 0, -1, -2, -3, or any other negative integer would be a counterexample to that statement. So a student makes the following conjecture. The difference of any two numbers is always smaller than the larger number. Find a counterexample to disprove the student's conjecture. So we remember that the word difference means to subtract. So the difference of any two numbers is always smaller than the larger number. So let's just pick a random number. So like 9 minus 5, the difference of those two numbers is 4. Is that smaller than the larger number? Well, yes, 4 is smaller than 9. So that's true. So now we need to think about examples that would make that false. So what about 9 minus 0? 9 minus 0 is 9, which is not smaller than the larger number. That 9 is not smaller than 9. So that 9 and 0 would be a counterexample. Another counterexample would be like 9 or 19 and negative 3. 19 minus negative 3 is 22. 22 is not smaller than 19, so that would also be a counterexample to that problem, or to that conjecture. Please sign up for your teacher talk and then start working on the practice. Thank you.